In the deepest laboratories on Earth, scientists have stumbled upon discoveries that defy every known rule of reality. They have found particles that seem to remember the future, information that travels backward through time, and objects that exist in many places at once until someone dares to look. These are not tales of science fiction. They are real quantum paradoxes that have forced the brightest minds to question whether reality itself might be an illusion. We are about to step into 26 of the strangest and most unsettling puzzles in physics, where consciousness might create the universe, where your choices could rewrite the past, and where the simple act of looking can tear holes in the fabric of logic. Prepare to have everything you know about existence shattered. A single photon of light moves toward two narrow slits cut into a metal barrier. It seems simple enough. The photon should pass through one slit or the other, like a marble rolling through a doorway. But quantum mechanics has no respect for such simplicity. When scientists fire individual photons at the barrier, something impossible occurs. Each photon appears to pass through both slits at the same time, creating an interference pattern on the screen behind it. The signature of waves colliding with themselves. This should be impossible. A single particle cannot occupy two locations at once. Yet there it is, the evidence glowing on the detector screen. Bright and dark bands formed by waves reinforcing or cancelling each other. It is as if the photon took every possible route through both openings at once. Then comes the truly disturbing twist. The moment scientists place a detector at one of the slits to observe which path the photon takes, the interference pattern disappears. The photon instantly behaves like a normal particle again, passing through only one slit. It's as if the photon somehow knows it is being watched and changes its behavior accordingly. Imagine a criminal who only breaks the law when no one is watching. Install a camera and they become a model citizen. Only this time, the criminal is a fundamental particle with no mind, no awareness, and no reason to know it's being observed. And yet, it does. Scientists have tried every possible way to trick these particles. They have built detectors so delicate they barely touch the photons, measuring them so gently that the photons should never even notice. But nothing works. It's as if the universe itself has an all-seeing eye that knows exactly when we try to lift the veil of reality. The implications go far beyond physics and into philosophy. If particles change their behavior when they're observed, what does that say about the nature of existence? Were the photons always moving through both slits, simply waiting for us to make them choose? Or do they truly exist in multiple states at once until our act of measurement collapses them into a single truth? For decades, physicists have struggled to explain this mystery. Some have suggested hidden variables that secretly determine the outcome. Others imagine parallel universes branching endlessly, where every possible result happens somewhere. A few even propose that consciousness itself shapes reality through the act of observing it, yet none of these theories feel complete. The double-slit experiment remains as baffling today as it was more than a century ago, and the deeper you think about it, the more unsettling it becomes. If the tiniest particles of the universe have no definite properties until they are observed, then what does that mean for the atoms in your body? For the chair beneath you? For the world itself when no one is watching? Each photon leaves its mark on the screen, a silent pattern that defies explanation. Scientists record the data, aware that they've glimpsed something that shatters the foundations of what we call reality. But this is only the beginning of quantum strangeness, because what happens when we observe these particles becomes far more disturbing when light itself appears to make choices based on decisions that have not yet been made. For centuries, light has been playing a cosmic game of hide-and-seek with human understanding. Isaac Newton once believed light was made of tiny particles, minute bullets speeding through space. This view explained why light travels in straight lines and casts sharp, crisp shadows. But experiments soon showed that light could bend around corners and form interference patterns, behaviors only waves can produce. For 200 years, physicists argued fiercely over light's true nature, refusing to accept that it could be both a wave and a particle at the same time. Then came the quantum revolution, and with it, an even more disturbing truth. Light doesn't merely act like a wave or a particle. It becomes whichever one the experiment demands. When scientists design an experiment to detect particles, light obliges by arriving as tiny packets of energy called photons. When they build a setup to detect waves, light transforms into rippling electromagnetic fields. But here is where reason begins to fracture completely. Light seems to make this choice based on what the observer plans to measure, even before the measurement occurs. Researchers can prepare light in one configuration, then change their detection method at the very last instant. Somehow, light already knows what's coming and changes its behavior to match. It's like a chameleon that doesn't just blend into its current surroundings, but into surroundings it hasn't even seen yet. Except this chameleon is every photon in existence, constantly shifting its identity based on future choices that may or may not even happen. No one knows how or why. There is no message traveling from the detector to the photon, no hidden signal or communication between them. Yet somehow, across the vast silence of reality, light always seems to know what we intend to do, before we've even done it. Yet the correlation is always perfect. No matter how the experiment is set up, light arrives in exactly the form needed for the test that awaits it. And this strange behavior doesn't just live in physics laboratories. It happens constantly in every interaction between light and matter. When you look at a red rose, the photons striking your eyes are already deciding whether to act as waves or as particles, depending on how your vision detects them. The very color red exists because light chose to behave as discrete packets of energy that match the way your eyes receive it. Scientists have tried to catch light in the act of transforming, to freeze the moment when it switches between being a wave and a particle. They have built detectors capable of changing their measurements faster than light itself can move. They have used quantum methods designed to measure photons so delicately that their natural state should remain untouched. Every attempt has failed. Light seems to exist in a strange suspended state, a superposition of all possibilities, until the instant measurement forces it to decide. The equations describing this dual nature work flawlessly. Physicists can predict exactly how light will act in any given experiment, yet they still cannot explain how a photon knows what kind of measurement awaits it. The mechanism behind this perfect awareness remains as mysterious as consciousness itself. And this is not just a philosophical riddle. Modern technologies, lasers, LEDs, solar cells, all rely on manipulating light's dual nature. Our civilization literally runs on a phenomenon we cannot truly comprehend, a quantum mystery that challenges the very idea of objective reality. But light's identity crisis grows even darker when we learn that particles can apparently make choices about their past behavior, influenced by measurements that have not yet occurred. In a quiet laboratory, a photon begins a journey that will test the limits of cause and effect. The setup appears simple. Scientists split a single photon into two entangled twins, two particles bound by a connection so deep that distance cannot break it. One photon travels toward a screen that will reveal whether it behaved as a wave or a particle. The other photon moves to a distant detector, where researchers can later choose whether to keep or erase information about its path. Here, time itself starts to lose meaning. The first photon strikes the screen and leaves its mark long before scientists make any decision about its twin. According to common sense, the result should already be locked in. The photon should have acted as either a wave or a particle. End of story. But quantum reality doesn't follow common sense. Hours, days, even years later, when researchers finally examine the second photon, their decision seems to reach backward through time and determine what the first photon had already done. If they choose to preserve the path information, the original photon reveals it acted as a particle all along. But if they erase that information, an interference pattern emerges, proof that the photon behaved as a wave. It's like developing a photograph and discovering that the image changes based on decisions you make long after pressing the shutter. The picture on the film somehow adjusts itself to match your future choices about how to process it. Physicists have stretched this effect across immense distances, yet the connection between entangled photons remains instantaneous and unbroken, as if reality itself bends to preserve its own mysterious consistency, no matter how far or how late we look. Scientists have now taken these experiments to unimaginable scales. They have sent photons across hundreds of miles, with measurement decisions made on opposite sides of the planet. Yet the correlation remains perfect. A choice made in Tokyo can instantly affect a photon that reached New York hours earlier. The most haunting versions of these experiments reach into the stars themselves. Imagine a photon born in the heart of a distant quasar billions of years ago, traveling across the cold void of space before finally arriving on Earth. Scientists can split that ancient light and delay their decision about how to measure it until long after the photon has already been detected. And still, according to the results of quantum eraser experiments, our decision today determines whether that photon behaved as a wave or a particle during its billion-year journey across the universe. This is not a thought experiment. It has been tested in multiple laboratories, and the results are consistent. Somehow the future seems to reach backward, shaping the past at the quantum level. Information does not care about time's arrow. It flows both ways, as freely backward as forward. The implications are staggering. If quantum decisions can ripple across years or centuries, what stops them from stretching across millennia? Could our measurements today be rewriting the behavior of particles that existed before Earth itself was born? Are we, without knowing it, reaching back to influence the quantum seeds that shaped the early universe? Some physicists insist this does not prove time reversal, only that particles share strange, non-local connections, the same spooky action at a distance that once baffled Einstein. Yet the mathematics hints at something far deeper. It suggests a cosmos where the future can edit the past, where the unfolding story of reality is written by observations that have not yet occurred. The photon finishes its impossible voyage, carrying information that seems to defy the very flow of time. But the true dread begins when we realize this effect might not be limited to single photons. It might be woven into the structure of the universe itself. Every quantum measurement could be a delayed choice, stretching across the fabric of space and time. One of the greatest physicists of the 20th century, John Archibald Wheeler, imagined an experiment so disturbing that it took decades before technology could make it real. Picture a lone photon heading toward a beam splitter, a device offering two possible paths. Normally, the photon would have to choose one route or the other before moving on. But Wheeler imagined something more unsettling. What if scientists could decide how to detect the photon only after it had already passed the beam splitter? The setup sounds like science fiction. A photon approaches the crossroads and must decide whether to act like a particle, taking a single path, or like a wave, exploring both simultaneously. Yet the experimenters make their choice only after the photon's journey is seemingly complete. When physicists finally carried out Wheeler's delayed choice experiment, the results were every bit as disturbing as he had foreseen. The photon's behavior depended entirely on choices made after it had already traveled through the system. If the detectors were configured to find a particle, the photon retroactively became one. It had taken a single path all along. If the detectors were set to reveal wave behavior, an interference pattern appeared, showing the photon had explored both paths at once. It's like watching a movie where the ending changes every time you decide how you want it to finish. Except you make that decision after the movie is already over, and somehow the entire story rewrites itself to match your future choice. Even the timing doesn't seem to matter. Scientists can delay their decision by minutes, hours, or theoretically by any span of time. Until that choice is made, the photon remains suspended in quantum limbo, neither particle nor wave, its history undecided, waiting for human consciousness to determine what it always had been. Wheeler then expanded the idea to cosmic scale. Imagine light from a faraway galaxy passing around a massive star before reaching Earth. Gravity bends its path, creating two possible routes, just like the beam splitter in a lab. According to Wheeler's logic, we could, in theory, perform an experiment today where our present measurement decides whether that photon took one path or both during its million-year voyage through the cosmos. This idea leads to one of the most unsettling possibilities in all of science, that consciousness itself might reach backward through time to rewrite the quantum history of the universe. Every act of observation could be collapsing wave functions that existed long before the Earth was even formed. We may, without realizing it, be deciding whether photons from the cosmic microwave background, the ancient afterglow of the Big Bang, behaved as waves or particles over 13 billion years ago. Mathematically, quantum mechanics handles these paradoxes with flawless precision. The equations always predict the correct results for delayed choice experiments, but the reality behind those numbers refuses to make sense. How could a photon possibly know what kind of measurement lies in its future? How can information flow backward through time without breaking the laws of cause and effect? Each successful experiment deepens the mystery, adding another fracture to our understanding of temporal order. The photon arrives at the detector carrying a history that was decided by a future event that had not yet happened when its journey began. And yet, the horror of these delayed choices is nothing compared to what comes next, when we realize that observers themselves might be trapped within the same quantum uncertainty. In the strange world of quantum mechanics, observation does not merely reveal reality, it creates it. Most of us imagine observation as passive, like watching a movie without changing the story. You open your eyes, light enters, and your brain interprets the world around you. But at the quantum scale, this simple act becomes cosmic. The very act of looking appears to bring the universe into existence. Consider an electron orbiting its nucleus. Before you measure it, that electron does not occupy any single position or speed. Instead, it exists as a shimmering cloud of probabilities, a ghostly fog spread across every possible location and state. Mathematics captures this precisely in what physicists call the wave function, an equation describing every potential property the electron might possess. But the instant you attempt to observe it, everything changes. The vast field of possibilities collapses into a single definite point. The wave function dies, and one reality emerges. Every other potential version of that electron, everywhere else it could have been, vanishes as though it never existed. The electron becomes real, but only at the cost of destroying countless other possibilities. This is not because our instruments are clumsy or disruptive. Physicists have designed exquisitely delicate measurements that barely disturb the particles they study. Yet the collapse still occurs. Reality seems to crystallize out of pure potential at the moment consciousness meets it. Imagine the universe as a vast simulation that only renders what you look at. When you face one direction, your surroundings appear vivid and detailed. But everything outside your view exists only as raw code, unrealized potential, waiting for attention to bring it to life. Turn your head, and the code instantly becomes landscape, sky, and light, as though it had been there all along. This unsettling analogy stretches far beyond the laboratory. If electrons only become definite when observed, what of the atoms that make up your body? Are they too suspended in possibility until consciousness locks them into being? What exactly counts as an observer powerful enough to collapse a quantum state? Some physicists believe that conscious awareness itself is the missing ingredient, that reality depends on a thinking mind to exist at all. Others argue that any interaction between quantum systems, no matter how small, counts as a kind of observation, meaning consciousness is not required. But neither view solves the central puzzle. Why does reality seem to need something to look at it before it becomes real? The Copenhagen interpretation, developed by Niels Bohr and his colleagues, embraces this mystery rather than explaining it away. It claims that asking what happens before measurement is meaningless, like asking about the sound of one hand clapping. Reality, according to Bohr, exists only in the interaction between the quantum and the classical, between possibility and observation. But this view leads to even deeper questions. If reality does not exist until it is observed, what was the universe doing for the billions of years before conscious beings appeared? Were galaxies, stars, and planets floating as vast probability clouds, waiting for an observer to bring them into focus? Did existence itself lie dormant, asleep in potential until life opened its eyes? Each act of measurement, each moment of awareness, seems to perform the same ancient miracle, pulling a single thread of actuality from an infinite sea of possibilities, creating one reality while extinguishing all the others that might have been. In the instant an electron collapses into its measured state, it becomes truly real, anchored in existence in a way it never was before awareness touched it. Yet even that unsettling revelation pales beside the terror that follows when two observers witness entirely different realities emerging from the same quantum event. This is the essence of Wigner's friend paradox, a thought experiment that tears the concept of objective truth apart. Imagine your friend sealed inside a perfectly isolated laboratory conducting a quantum measurement on a spinning particle. For them, the result is definite. The particle spins either clockwise or counterclockwise. They record their finding, believing the mystery resolved and the wave function collapsed. But from your vantage point outside the sealed room, quantum theory demands that you treat the entire setup, your friend, the apparatus, and the particle, as a single quantum system still in superposition. To you, your friend exists in two contradictory realities at once. One where the particle spins clockwise, and another where it spins counterclockwise. This is where reason begins to fracture. Both you and your friend are correct according to the mathematics of quantum mechanics, yet your conclusions about reality cannot both be true. Did the particle collapse when your friend observed it, or only when you opened the lab door? If your friend truly remains in superposition, then they are somehow aware of both outcomes simultaneously. An impossible dual consciousness defying logic and biology alike. It's like two surveillance cameras filming the same event, yet one shows a crime while the other shows an act of kindness. Both perspectives are valid within their own frame, but they can never be reconciled into a single consistent truth. Modern quantum experiments have brought this paradox out of imagination and into the laboratory. Physicists have built systems where multiple observers measure entangled particles and record results that contradict one another, each description accurate according to the equations. The universe, it seems, allows mutually exclusive truths to coexist. Some researchers believe consciousness itself holds the key, suggesting only a conscious observer can collapse a quantum system into a definite state. But that raises an even deeper mystery. How could awareness possess powers that override the mathematical fabric of the universe? Others argue that quantum mechanics ceases to apply to large-scale systems like people, yet no one can pinpoint where the boundary between quantum and classical truly lies. The many worlds interpretation takes a radical path. It suggests both you and your friend are right, but in different branches of reality. Each observation splits the universe, creating countless versions where every possible outcome occurs. In one world, the particle spins clockwise, in another, counterclockwise. Your consciousness follows one path, while another version of you experiences the alternate outcome. The cost of solving the paradox is an infinite multiplication of realities. Every measurement doesn't collapse possibilities. It births entire universes. At the heart of this labyrinth lies a contradiction so profound, it threatens the very foundation of science. Quantum mechanics works. Its equations predict atomic behavior with near-perfect accuracy and power, modern technology from lasers to computers. Yet its logic remains fractured, describing a universe that refuses to settle on a single reality. Particles are waves of probability until observed. Observation depends on consciousness, and consciousness might depend on the very reality it helps define. In this endless circle, truth itself dissolves, leaving us with a haunting question. Is reality created by the universe, or by the mind that dares to look at it? Wave functions evolve in graceful, predictable motion, guided perfectly by the Schrödinger equation, rising, fading, and weaving through one another in precise harmony. But the instant a measurement occurs, something catastrophic shatters that smooth progression. The elegant, deterministic flow collapses without warning. In a blink, all possible outcomes vanish except one. Physicists call this the collapse of the wave function, and it violates the very equations that define quantum mechanics. Imagine an orchestra performing a flawless symphony. Every instrument follows its score, the melody unfolding in mathematical perfection. Then, abruptly, the musicians stop obeying the notes and each begins to play something random, discord, chaos. Yet somehow, to the listener, only one clear tune is heard. That is the riddle of quantum measurement. When and how does this collapse happen? What qualifies as a measurement? And why does the quantum world of fluid possibilities transform into the definite reality we experience? Physicists have proposed countless answers, each stranger than the last. Some claim that consciousness itself triggers collapse, that awareness forges reality by observing it. Others argue that large systems automatically lose their quantum behavior through interactions with their environment, a process called decoherence. Still others insist that the wave function never collapses at all, but instead splits into parallel realities, each containing every possible result of every measurement. Each of these answers spawns new paradoxes. The consciousness theory grants human awareness almost divine control over the fabric of existence. Decoherence explains why we never see superpositions in daily life, but cannot explain why individual measurements yield single, definite results. The many worlds view preserves mathematical consistency, but only by invoking an infinite number of parallel universes. And lurking beneath them all is an even deeper problem. What happens to the measuring device itself? Every detector is made of atoms, and atoms obey quantum rules. When a detector clicks to signal a captured particle, what makes its own wave function collapse into the clicked state? This question leads to an infinite chain. Each quantum system requires another observer to fix its outcome, which in turn needs another observer, and so on without end. The measurement problem remains suspended between two worlds, quantum possibility and classical certainty, waiting for a final answer that might never come. And yet, the real terror lies not in collapse, but in what superposition truly implies. Textbooks describe it calmly, a particle existing in multiple states at once until measured. But the idea, when taken seriously, is nightmarish. Quantum mechanics tells us that before observation, an electron spins both clockwise and counterclockwise. A photon travels along every possible path, and every atom lives in countless overlapping conditions. Now extend that to yourself. The atoms in your brain follow quantum laws. That means your neurons exist in simultaneous states, firing and not firing, deciding and hesitating, until something, perhaps consciousness itself, collapses them into a single experience. If your mind emerges from those quantum processes, then your thoughts too might exist in superposition. You could be both joyful and sorrowful, remembering and forgetting, choosing and refusing all at once until the act of awareness focuses you into one version of reality. Imagine standing inside a vast hall of mirrors where each reflection shows a different version of you making different choices. You can see only one reflection at a time, but quantum mechanics suggests all of them exist, real and complete, until your gaze fixes upon one. That act of looking decides which you becomes actual. The implications reach far beyond the human mind. If nothing in quantum theory forbids superposition on a larger scale, then why stop at atoms or brains? Entire cities could exist in overlapping configurations, built and ruined, bustling and silent, thriving and extinct, all at once. Planets might spin in multiple states. Galaxies might shimmer in every possible arrangement. And the universe itself could exist in endless layers of possibility. This is not idle speculation. Scientists have already created superpositions in increasingly large systems, molecules, mirrors, even microscopic mechanical devices, pushing the boundary between the quantum and classical closer to our everyday world. Each new experiment reminds us that the line dividing possibility from reality may not exist at all. Perhaps the world around us, solid and familiar, is nothing more than a superposition waiting for someone or something to look and make it real. They've already coaxed vast molecules, hundreds of atoms bound together into quantum superposition, objects large enough to almost see with the naked eye existing in two or more states at once. Tiny mechanical resonators have been built that vibrate and do not vibrate simultaneously, trembling at the edge of two realities. Each experiment pushes the boundary between the microscopic and the macroscopic, erasing the imagined wall between quantum strangeness and ordinary life. Some physicists are now attempting something that once seemed impossible: to place living organisms into superposition. They wonder whether bacteria, viruses, or even multicellular creatures can exist in overlapping states of life and death, activity and stillness, consciousness and void. If they succeed, Schrödinger's cat will no longer be a parable but a fact of laboratory science, a living being hovering between existence and annihilation. Yet such experiments raise a question that chills the soul. If a being exists in multiple states, which one is the true self? Are all versions equally alive, equally aware? When superposition collapses, do the other selves perish in silence, or do they continue in parallel worlds we can never reach? Mathematics handles these questions neatly. Superpositions interfere, evolve, and collapse according to flawless equations. But the subjective reality of such a state remains utterly unknowable. What does it feel like to be partly dead and partly alive? A consciousness spread thin across universes. Every quantum measurement performs an invisible act of destruction. Infinite possibilities are born, and then all but one are slain. The collapse of the wave function is not gentle. It's an execution. It kills every world but one and calls the survivor reality. We move through life atop a field of corpses. the dead remains of possibilities that never came to be. Schrödinger intended his cat thought experiment to mock this absurdity. He imagined a simple device, a Geiger counter, a hammer, a flask of poison, connected to a single radioactive atom. If the atom decayed, the counter would trigger the hammer, shatter the vial, and kill the cat. Because radioactive decay is a quantum event, the atom exists both decayed and undecayed until measured. Thus, so does the cat, both alive and dead in perfect superposition. Schrödinger meant this as satire, a proof by contradiction that quantum mechanics must break down for macroscopic things. Surely, he thought, a real cat could not occupy such a grotesque halfway state. But modern physics has betrayed Schrödinger's skepticism. Decades of experiment have revealed no limit to quantum behavior. There is no hidden rule declaring that large things must act classically. The transition from quantum to classical appears to be a matter of scale, not law, of environmental interference and decoherence, not impossibility. With sufficient isolation, even vast systems, mirrors, diamonds, and perhaps someday living tissue, can slip into superposition. If that is true, then the cat's paradox becomes our own. There is nothing in the equations preventing you from existing in superposition right now. Your atoms simultaneously composing countless different versions of yourself. Breathing and not breathing, awake and asleep, alive and gone. Your mind too would branch accordingly, each thought dividing into infinite parallel echoes. The unsettling truth is that you have no way to tell. Every time you observe another person, or even glance in the mirror, you collapse a cloud of probabilities into one fragile outcome. Until that act of observation, they exist in all possible states, healthy and ill, smiling and weeping, alive and dead. The stranger on the street corner, the friend who hasn't returned your call, your neighbor behind a closed door, all drift as quantum ghosts, their realities unresolved until witnessed. Perhaps this is the true horror of quantum superposition. Not that particles behave unpredictably, but that everything, including life, thought, and identity, might hover in a shimmering haze of potentiality. The world around us feels solid only because our minds are continuously collapsing it into form, selecting one thread from an infinite weave of possibilities. And when we look away, when consciousness lapses, who can say whether it stays fixed or returns quietly to the sea of all things that might be? The implications ripple through every layer of existence. Your coffee cup, resting quietly on the table, sits in a ghostly haze of probability, simultaneously full and empty, hot and cold, cracked and unbroken until you look at it. The traffic light at the end of the street shines red, yellow, and green all at once. The money in your bank account exists in every possible amount until you check the balance reality. It seems is not solid. It's statistical a vast, invisible cloud of potential, where everything exists in every possible state until consciousness touches it. Your home is both spotless and in ruin, your phone battery charged and dead, your refrigerator stocked and bare. Every observation you make collapses infinity into one fragile moment of certainty. The act of living becomes the act of measurement. Each glance, each heartbeat, slicing through the fog of probabilities to create the single thread of time you call your life. But here's the truly unsettling thought. If consciousness causes reality to collapse, what happens when consciousness sleeps? When the mind drifts into dreams or sinks into a coma, does the world hold its breath? Does everything remain suspended, neither real nor unreal, waiting for awareness to return? Every sleeper, every wandering thought, could be adrift in quantum limbo, alive and dead, awake and dreaming, all at once. And in that strange idea lies one of the deepest interpretations of quantum mechanics, that the entire universe exists in superposition, and only the fragile bubble of consciousness collapses it into something definite. We walk through a fog of ghostly possibilities, our awareness, carving shape and meaning into an ocean of quantum potential. Schrödinger's cat, both alive and dead, is not just a metaphor in a sealed box. It's the reflection of reality itself. Every unopened door, every unobserved moment is a world still undecided, and yet, even this eerie duality is nothing compared to what comes next. Because superposition is only half the story. The other half is entanglement. Albert Einstein called it spooky action at a distance. And for once, even he underestimated the spookiness. When two particles become entangled, they are no longer two, They become a single system, one wave of existence stretched across the universe. Measure one, and you instantly determine the other no. Matter how far apart they drift, this isn't mere coincidence, it's instantaneous influence, a link that defies distance and mocks the speed of light. The experiment seems harmless enough. Two particles created with opposite spins, sent racing in different directions. Classical physics would say one spins clockwise, the other counterclockwise, each defined from the moment of birth. But quantum mechanics whispers something stranger. Before observation, neither particle has chosen. They exist together in an entangled superposition, a shared identity spread across space itself. Even when separated by millions of miles, they remain one system, as if the fabric of space does not apply to them. When one particle is measured spinning clockwise, the other doesn't merely happen to spin the other way, it becomes that way. Instantly, even if it's orbiting Jupiter while its twin rests on Earth. At that exact moment, the universe makes a choice. It's as if two coins are flipped at opposite ends of the world, but neither shows heads or tails until one lands. And when it does, the other instantaneously takes the opposite face. No signal, no waiting. Just one decision echoed across space. Scientists have pushed this strangeness to the limits. They've entangled photons across cities, across mountains, across open sky. They've watched the connection hold, flawless, immediate, unbreakable. They've sealed every loophole, tested every trick, and still, the mystery remains. Something beneath space itself is at work, a hidden unity, a silent coordination that refuses to obey the rules of distance and time. And it leaves us with one haunting possibility. If two particles can remain connected across light years, perhaps everything that was ever connected still is. The universe appears to tolerate something no law of physics should allow: instantaneous connection across impossible distances. 2 points in space, separated by light years, yet tied together by invisible threads that ignore every boundary of time and distance. This single truth fractures the ancient idea of locality, the comforting belief that things can only influence what lies close to them if entangled. Particles can affect one another across the breadth of the cosmos. Then, separate objects may not truly exist at all. Everything, every atom, every star, every living thing might be joined in an unseen quantum web, a tapestry of correlations woven through the darkness where the space between things is nothing but an illusion. Some physicists whisper that this may be reality's true structure, not a universe of individual parts interacting across a void, but one continuous unified quantum field whose apparent separations are tricks of limited perspective. Others dare to go further, suggesting that entanglement isn't confined to space at all, that it can reach backward through time. That when you measure one particle today, your observation may ripple into the past, adjusting the history of its partner to match what you will one day see. Every interaction in nature, every collision, every flicker of light, every heartbeat and breath creates new entanglements, linking objects that may never again share a place or a moment. The cosmos is constantly weaving an endless network of invisible relationships, a web that may stretch from your hands to the birth of the stars themselves. If this is true, then separation, the idea that one thing can ever be apart from another, is the deepest illusion of all. But for Einstein, that illusion was sacred. The man who bent space and time into a single continuum refused to accept a universe that abandoned cause and locality. He believed in a reality that existed independently of human measurement, a cosmos that did not need to be watched to be real. Quantum mechanics violated that faith. It claimed that until observation, particles had no definite properties, no position, no spin, no identity, only possibilities waiting to collapse. To Einstein, this was madness. He was convinced the theory was incomplete, that hidden variables, unseen but real, must exist to restore determinism and sanity to physics. With Boris Podolsky and Nathan Rosen, he designed a challenge: the EPR paradox. Two particles created together, then flung in opposite directions across space. Measure one, and the other's properties are instantly known. Einstein argued that this was proof of something missing. If quantum mechanics were correct, information would have to travel faster than light, an unthinkable violation of his own relativity. No influence could leap across the void instantly. He insisted the particles must carry predetermined instructions, a secret script written at birth. That script was what he called the hidden variables for decades. The debate raged only in theory. Then in the 1960s, a quiet Irish physicist named John Bell found a way to test it. Bell derived a simple, ruthless inequality, a mathematical boundary separating Einstein's world from the quantum one. If hidden variables existed, experimental results would obey certain limits. But if the universe was truly quantum, those limits would be broken when the tests were finally done. The results were merciless. Nature violated Bell's limits, not once, not barely, but exactly as quantum mechanics. Predicted reality itself refused to be. Local entangled particles did not wait for signals. They responded instantly, as though distance simply wasn't real for them. It was like discovering that identical twins don't merely share genes but share thoughts, reacting in perfect harmony, even when separated by planets or galaxies. Except these twins aren't people, they are particles that have never met, and their shared behavior extends across billions of miles. The violation of Bell's inequalities was more than an experiment. It was a revolution in the meaning of real. It proved that the universe is non-local, that space and time are not the ultimate stage of existence, but the surface of something deeper, a single interconnected whole where every event, no matter how distant, may still whisper to every other. Modern physicists have tried to rescue Einstein's realism. They've randomized detectors, sealed labs from outside influence, closed every loophole that might explain away the correlations, and still, the quantum threads hold the universe, it seems, is one great body, its every atom entangled with every other, a silent, shimmering unity that no distance can divide. They've measured particles whose strange bond seemed to form after the decision to measure them was already made, leaving no room for preparation or hidden communication. Every new experiment confirms the same impossible truth. The universe is not local. Distant things remain bound by invisible threads that move faster than light. But information isn't traveling between them. Instead, both remain part of a single quantum whole that ignores space and time entirely. Einstein's greatest fear has now become physics' most unshakable reality. The cosmos itself allows spooky action at a distance, forcing us to confront the possibility that separation and independence are illusions. The correlations between entangled particles continue to break Bell's limits, proving that reality refuses to follow even Einstein's most sacred rules. And that's when the mystery turns terrifying. Bell's theorem doesn't just describe strange behavior, it suggests that reality itself does not exist until someone chooses to observe it. John Bell built a mathematical argument showing that the world we believe in cannot exist the way we imagine. His theorem leaves us facing three nightmarish possibilities, each one defying reason. The first concerns locality, the idea that distant events cannot influence each other instantly. If particles possess real properties before we measure them, then their perfect correlations demand communication faster than light. Imagine two magic 8 balls giving opposite answers at the same time, even when they sit on different planets. Either they are communicating across space instantly, or their answers don't exist until you shake them. The second assumption is realism, the belief that physical properties exist whether anyone looks or not. If locality must hold, then Bell's experiments prove that particles have no definite state until observed. The universe rests in a sea of potential, becoming real only when awareness touches it. The third is freedom of choice, the notion that experimenters truly decide which measurements to perform. Some physicists believe the entire universe is predetermined, including our supposed free decisions. In this superdeterministic cosmos, every choice, every particle, every thought was written into the initial conditions of time itself. Each escape from Bell's theorem carries unbearable consequences. Faster than light signals destroy causality, the bedrock of space and time. A reality without definite properties dissolves the world into pure possibility. A predetermined universe erases free will entirely. Most physicists choose to abandon realism, keeping locality intact. But that choice quietly transforms science itself. Physics becomes not the study of an objective world, but a map of how consciousness experiences it. The universe turns into a mirror that reflects the act of observation. Bell's theorem doesn't merely challenge equations, It threatens the foundations of material reality. The cosmos now appears inseparable from the observer, woven together in ways that defy logic and comfort alike. The mathematics is unbroken. The conclusion, unavoidable. Reality violates the principles we once called sacred: locality, objectivity, and existence itself. But Bell's nightmare deepens further. In a twist straight from Alice's Wonderland, quantum mechanics reveals that particles can detach from their own properties. Just as the Cheshire Cat's grin lingered after the creature vanished, a particle can send its traits away from itself. Experiments using neutron interferometers have shown this unsettling divide. Under precise conditions, a neutron can travel through one path, while its magnetic moment journeys through another, the particle and its essence separated across space, yet still bound in unity. This isn't illusion or trick. Multiple laboratories have confirmed the effect. Detectors register the particle in one place, its magnetic property somewhere else. Imagine your shadow stepping away, walking independently, interacting with objects while you remain still. And yet, that shadow remains undeniably yours. In the quantum world, such separations are not fantasy. They are evidence that reality, as we experience it, is an intricate performance of divided selves, matter and meaning, wandering through a universe that refuses to stay whole. They're measurable realities, not illusions, tangible physical, quantities that can be detected and manipulated in places where the particle itself simply isn't. The secret behind this strange disembodiment lies in what physicists call weak measurements, observation methods so impossibly gentle they touch the quantum world without breaking it. These subtle detections let scientists follow a particle's traits without collapsing its entire wave of possibilities. Somewhere between quantum superposition and ordinary existence, matter and property diverge, traveling separate paths through space. And the effect doesn't stop with a single attribute. Researchers have now separated entire sets of characteristics: spin, magnetic moment, even electric charge, sending each along a different route. The particle becomes a kind of quantum ghost, while its properties drift through the laboratory like independent spirits, haunting space on their own. The implications unravel the very idea of what a thing is. If a particle can exist apart from its defining traits, then what exactly are we observing? Are particles actual objects with built-in qualities? Or are they fleeting alignments of phenomena, momentary meetings of traits that usually coincide but don't have to? It's like discovering that a person could send their thoughts, memories, and emotions to wander the world while their body remained motionless. The form would stay behind, but the essence, the identity, could live elsewhere, perceiving, reacting, even changing the world in its absence. Some scientists see opportunity in this eerie separation. By dividing sensitive properties from the particles themselves, they hope to build new tools for ultra-precise measurements, probing fragile environments without disturbing them. Detached magnetic fields, electric moments, or spin orientations could explore conditions too delicate for full particles to survive within. Yet beneath the promise lies something existential. If properties can travel independently of the particles that host them, then the boundary between an object and its attributes dissolves. A thing is no longer a collection of fixed properties, but a temporary truce between independent phenomena, a delicate alignment that can split apart and reform like ghosts meeting in the dark. In the quantum world, identity itself becomes negotiable. Matter is not what it seems. It is a whisper of relationships, briefly holding together before wandering off again into the infinite uncertainty of space. Recent theories whisper that the quantum Cheshire Cat is not a laboratory trick, but a shadow of something deeper, something woven into the very grammar of the universe. These effects, physicists now believe, appear whenever a quantum system is only partially measured, when fragments of its coherence survive, even as other parts collapse. In these delicate experiments, the neutron glides through one arm of the interferometer, while its magnetic moment drifts silently through another, both completing their journeys to detectors that confirm what should be impossible: a single being divided, existing in two distinct places at once. But even this ghostly separation is only the prelude to something more disturbing. For the true terror of quantum reality lies not in divided particles, but in the realization that the outcome of any experiment depends entirely on how you choose to look at it. Reality, it seems, is contextual. It doesn't merely reveal itself. It rewrites itself around the questions you dare to ask. Contextuality sounds abstract, but its implications strike at the heart of existence. The same particle, the same setup, can produce entirely different results depending on what other measurements you perform beside it. It isn't that the instruments are flawed or that the universe plays dice badly. The truth is worse. The properties themselves depend on the act of observation, bending and reshaping according to context, mocking the very notion of objectivity. Imagine trying to measure the spin of an electron. Classical intuition tells us it should have definite values in every direction, like a spinning top whose motion exists whether we watch or not. But quantum reality defies such reason. Measure the spin vertically, then horizontally, and you'll get one pattern of results. Reverse the order, and the numbers change. Not just the second reading, but the first as well. It's as if the mere intention to measure differently afterwards sends ripples backward through time, rewriting what was already true. Think of asking someone their favorite color. If you tell them you'll next ask about food, they might answer blue. But if you plan to ask about movies, they will have always preferred red. The answer doesn't exist until the context around the question defines it. Physicists have confirmed this nightmare experimentally. In tests with photons, electrons, and atoms, quantum systems have violated inequalities that all classical systems must obey, proving beyond doubt that properties depend on the context of measurement, change the surrounding conditions, and the particle's supposed attributes vanish or reappear, as if existence itself were a dialogue rather than a fact. Reality, under this lens, becomes conversational. It isn't a warehouse of objects with permanent qualities, but a vast web of potential relationships waiting to be awakened by observation. The universe, in this view, isn't made of things. It's made of questions. Some researchers argue that contextuality might explain nearly every quantum paradox. The dual nature of particles and waves, the strange link of entanglement, the collapse that turns possibility into presence. But this understanding replaces mystery with something far more chilling. If the universe is contextual even beyond the lab, then your very thoughts, memories, and sense of self might shift depending on how others perceive or measure you. Every observation reshapes what is real. Every question helps decide what was always true. And somewhere beneath it all, in the uncollapsed depths of the quantum world, every possible version of those questions and every possible answer is unfolding at once in countless parallel worlds, each carrying its own reflection of you. Every quantum event, and they unfold in uncountable trillions each second within every breath of space, splits the fabric of existence into countless threads. With every flicker of possibility, reality branches, blooming outward like an infinite tree made of mirrors and time. You are not one being, but a forest of selves, each walking a different corridor of possibility. Imagine a house of mirrors with no end, each reflection living its own life. In one, you turned left instead of right. In another, you never met the person you love. In a third, you never even existed, because the universe that bore you never conspired to let your parents meet. Every instant gives birth to new worlds that will never meet again. Each one equally real, equally alive, equally unaware. But the horror deepens when you realize that this branching does not stop at the surface of your choices. It runs through the blood, the bones, the fire of thought itself. The quantum storms within your cells split endlessly. Every neuron spark, every fleeting idea divides into parallel cascades of thought, each spawning a new mind that believes it alone is you. Across the infinite lattice of existence, there are versions of you that live blessed lives of miraculous luck. Cells that heal impossibly, particles that align to gift you joy and love and triumph. And there are others, infinitely more perhaps, that die in agony, struck down by cosmic rays, undone by unseen molecular failures, doomed by probabilities that turned cruel. Mathematics whispers that most versions of you die young, erased by quantum accidents before they ever understand why. Only a few survive long enough to wonder about survival itself, and perhaps that is the reason you are still here. Because consciousness, by its nature, can only exist in branches where the brain endures. In every other version, you have already fallen silent. Yet the equations reveal something stranger still. Even when systems should become too large, too tangled for quantum interference to persist, it sometimes does. Echoes remain, faint and disobedient, suggesting that these parallel branches, these ghostly worlds, may still bleed into one another. Reality, it seems, is not cleanly divided, but haunted by its own reflections. The multiverse may be not a theory, but a living fact, a ceaseless bloom of universes, all unfolding together. Every decision, every flicker of a particle, every neuron sigh creates another version of you that wanders off into its own infinity. You live all these lives at once, but remember only one. And so the branching continues, relentlessly, exponentially, birthing uncountable copies of your mind with each passing heartbeat. Most will never know the others exist, but the terror sharpens when we confront the logic of quantum suicide. If every outcome happens somewhere, then from your own perspective, death itself becomes impossible. Consciousness can only persist in the branches where it survives, no matter how narrow the odds. You would live on forever through increasingly improbable worlds, immortal, but imprisoned in an infinite sequence of survivals. Imagine a gun linked to a quantum randomizer. Each pull of the trigger decides, by quantum law, whether it fires or misfires. In a single universe, fate would be final. But in the multiverse, every outcome unfolds. In some worlds you die, in others the gun forever misfires. And from your own view, trapped within consciousness that can only exist where it remains intact, the click of survival echoes endlessly. A version of you always lives, always breathes, always opens their eyes again. And somewhere, across infinite mirrors of creation, the gun never fires. But this is where the paradox turns inward, where science brushes against something older and darker than reason itself. From your own point of view, there are no branches where you die. Those versions of you simply fall silent, their awareness extinguished like candles in unseen rooms. Only the branches where your consciousness endures can ever be known to you. To yourself, you would seem immortal, drifting always into the thin corridors of survival. Imagine playing Russian roulette with a revolver the size of a world, 1 billion chambers, a single bullet. And somehow the gun never fires. Again and again, you pull the trigger and wake to find yourself still here. To everyone else, it looks like luck. To you, it feels as if the universe itself refuses to let you go. This strange protection extends beyond choice and chance. In a quantum multiverse, there are always realities where the disease retreats, where the crash narrowly misses, where the final heartbeat stutters, and then, impossibly, continues. From your own perspective, you slip endlessly into the branches where death is delayed, where life stretches just one more moment further. But this so-called immortality is not a gift. It is a prison built from probability. As the years unfold, the surviving versions of you drift into increasingly impossible worlds, places where biology bends, where entropy hesitates, where your body becomes a patchwork of miracles that should not exist. Muscles knit themselves through quantum chance. Cells regenerate through coincidences so rare they border on divine. You live on, but each breath costs the universe a little more. Plausibility. Some physicists argue that this scenario cannot happen, that consciousness depends on classical brain processes, which do not splinter like quantum particles. Others quietly suspect that the very fact you exist to ask this question proves otherwise. They invoke the anthropic principle. We find ourselves only in universes where our existence is possible. Perhaps we already dwell inside one of those rare branches, the fragile thread where life emerged, where planets survived bombardment, where chaos allowed consciousness to bloom. The thought grows colder the longer you hold it. Maybe you are already experiencing quantum immortality. Every narrow escape, every unlikely recovery, every near miss that should have ended everything. Each might be another quiet divergence, another world that fell away while you continued forward alone. With every survival, you move deeper into improbable realms where reality twists just enough to keep you breathing. Immortality becomes an endless corridor with no exits, each step more impossible than the last. Yet even that nightmare pales before the deeper question waiting beneath. It, the question that haunts the foundations of physics. Does consciousness create reality, or does reality create consciousness? And what happens to us if we've misunderstood which came first? At the core of quantum mechanics lies a riddle known as the measurement problem. The equations of the universe evolve smoothly, predictably, until someone looks. And in that act of observation, everything collapses into definite form. The wave of possibility becomes a single outcome. But what counts as looking? Must a mind be present, or can reality collapse itself without us? Some interpretations whisper that consciousness is not a passenger but the driver. That before awareness arose, the cosmos existed only as a vast sea of probabilities, waiting for someone to notice it. Your act of perception may not just reveal reality, it may create it. If that's true, then you are both the observer and the architect, the dreamer and the dream. The universe might not exist in full until it is seen. Picture it as a film that begins only when someone presses play. Every frame, every moment, every event exists as a script of endless possibilities until your awareness calls it forth. What you choose to notice becomes what is real. Perhaps consciousness does not inhabit the universe. Perhaps the universe inhabits consciousness. But this explanation opens a darker corridor of thought, one lined with mirrors that reflect only uncertainty. If consciousness truly creates reality through the act of observation, then what becomes of the universe when you stop looking? Does the world remain standing while your eyes are closed? Or does it quietly dissolve back into quantum fog, waiting for you to wake and notice it again? When you gaze at the stars, are you seeing ancient light that has traveled for billions of years? Or are you creating that light in the very instant your awareness touches it? The question folds in on itself until cause and effect lose meaning. Yet the alternative is no comfort. If consciousness is not a creator, but an illusion, if awareness is merely the flicker of classical neurons performing quantum computations, then every thought, every feeling, every heartbeat of identity is nothing more than the echo of matter pretending to know itself. The self becomes a mirage cast by circuits of probability. Experiments have tried to pierce this mystery, isolating quantum systems from human eyes, watching whether the universe collapses even when no one is watching. The results whisper contradiction. Quantum states seem to choose outcomes whether or not consciousness is present. Reality, it seems, does not need witnesses, but perhaps it behaves differently when they arrive. Some physicists insist that consciousness and quantum physics cannot touch, that our minds are built from classical processes too crude to sense the shimmer of the quantum world. Others propose the opposite, that consciousness itself may be a quantum phenomenon, born from coherence and entanglement within the microscopic architecture of the brain. If that is true, then the boundary between observer and observed ceases to exist. Awareness becomes a participant in the experiment, a reflection looking into itself, both subject and object, in an infinite recursion. The mind observing the universe becomes the universe observing the mind, and so we are left suspended between two impossible possibilities. Either consciousness possesses supernatural power, sculpting reality with every glance, or it is a phantom conjured by lifeless matter, convinced of its own significance. In one vision, the cosmos exists because you see it. In the other, you are a trick of quantum machinery dreaming that it can see. But the puzzle deepens still further. For even if consciousness and reality are separate, something strange happens when the quantum world touches the classical one. The shimmer of superposition vanishes. The strange probabilities collapse into the crisp solidity of everyday life. Why does the world hide its quantum nature so carefully from us? Physicists call this process decoherence, the slow drowning of quantum order in the noise of the environment. Every photon, every air molecule, every magnetic field whispers a fragment of the quantum secret to the world, until the secret is no longer secret at all. Imagine trying to keep a secret in a crowded hall. At first, only you and one other person know. Then others overhear, then more, until the truth spreads too widely to remain private. The same thing happens to quantum systems. The more they interact with their surroundings, the faster their coherence is lost. The universe, it seems, cannot keep a secret for long. An electron's spin entangles with nearby atoms. Those atoms entangle with light. That light entangles with detectors, and detectors entangle with you. The web expands until the original superposition dissolves into the noise of everything else. This is why you never see your coffee cup in two places at once. The air, the light, the warmth of your hand are all conspiring to erase its quantum strangeness before you can notice it. But decoherence is not a solution. It is an evasion. It explains why superpositions become invisible, not why they become impossible. Mathematically, the universe should still contain all those possibilities, only entangled with everything around them. If a particle entangles with a detector, and that detector with a computer, and that computer with you, why should the whole chain not exist in superposition? The equations do not forbid it, yet we never see it happen. The boundary between the quantum and the classical remains unfixed, an invisible gradient where one fades into the other without a clear line. The transition appears continuous, as though the world gradually chooses solidity over possibility. Scientists have discovered that the rate of decoherence depends on the environment itself. In the coldest laboratories, isolated from air, sound, and light, quantum coherence can linger seconds, even minutes, inside fragile systems that should already have collapsed. But at room temperature, the collapse is nearly instantaneous. The world prefers definiteness when left in the open air. This suggests something quietly revolutionary, that the classical universe, the world we touch and trust, is not fundamental at all. It is an emergent illusion, rising like foam from the deeper sea of quantum uncertainty beneath it. Step by step, experiment by experiment, physicists are pushing that boundary outward, creating superpositions in ever larger objects, from clusters of hundreds of atoms to microscopic diamonds that hum in the vacuum between being and not being. Each success inches the dream closer, to glimpse the moment when the familiar world of matter gives way to the ghostly shimmer of quantum truth. But still, the central question remains unanswered. Why does the universe prefer to hide? Why does it trade infinite possibilities for the single solid story we call reality? Perhaps it is not reality that hides from us, but we who hide from it. Why do the whispers of the environment destroy coherence instead of weaving a greater harmony? Why does the universe not bloom into one vast entangled song? Each interaction could, in theory, expand the web of coherence until every atom shared the same shimmering thought, but instead, the song collapses into silence. The delicate rhythm of quantum unity drowns beneath the noise of the world. Somewhere between the infinitesimal and the infinite, there lies a boundary, a fragile threshold, where quantum strangeness fades into the soft normalcy of the classical world. No one can point to its exact coordinates. It does not lie in size or distance or mass alone. It is a gradient of exposure, a slow surrender to chaos. Every breath of air, every photon of light, every stray vibration conspires to erode coherence until the quantum possibilities curl inward and vanish from sight. Decoherence does not explain why reality chooses to hide, only how the hiding occurs. The deep shimmer of possibility dissolves into environmental entanglement, leaving behind the dull certainty of the classical world, a surface that conceals the sea beneath. The mathematics describe it perfectly, and yet the reason remains invisible. But even these mysteries pale before a deeper cosmic law, a principle so unyielding that breaking it would fracture the logic of existence itself. Information can never be destroyed. It may change its face. It may vanish into entropy or scatter across light years of vacuum, but somewhere, somehow it endures. For the universe does not forget, it only rephrases. Every process in quantum mechanics can be reversed. A scattered particle can unscatter. A wave function can refocus. An entangled pair can be disentangled. The universe behaves like a vast reversible equation, and within that equation, every detail, every choice, every flicker of being is preserved. Imagine the cosmos as an eternal library, its shelves stretching beyond galaxies. Every thought, every particle, every event is a book. And though the books may burn their ashes, still whisper the words they once held. The molecules of smoke carry the shapes of letters. The light of the flame encodes the rhythm of sentences. The air remembers the warmth of meaning. Nothing is truly lost, only rewritten in the strange language of transformation. If you burn a page, its story still exists. hidden in the motion of ash and light. The heat trembling through space. The vibration of atoms struck by the fire's breath. A godlike intelligence could gather the smoke, measure every photon, and rebuild the words exactly as they were. For the information remains scattered but immortal, and if this law holds for matter, then it must hold for mind. If your thoughts are patterns of quantum information, then every fleeting memory, every fear or secret dream becomes eternal, woven into the architecture of the universe itself. Your consciousness, your entire existence, may already be encoded in the infinite memory of the cosmos. This is where physics brushes against the divine. The conservation of information, so elegant in theory, becomes unbearable in meaning. For if nothing is forgotten, then the universe remembers everything. It remembers the birth of stars, the trembling of the first cell, the echo of every heartbeat that ever lived. All of it recorded every photon, a page, every atom, a syllable, every quantum fluctuation, a punctuation mark in the library of reality. Yet there is a shadow in this perfection. Black holes, the devourers of information, the cosmic furnaces where reality appears to lose its memory. When matter falls into a black hole, it carries its quantum story with it, the spin of particles, the arrangement of atoms, the hidden instructions of existence itself. And according to general relativity, that story ends there, swallowed beyond the event horizon, forever unseen, but quantum law forbids forgetting, and so the paradox begins. Stephen Hawking's discovery only deepened it. Black holes are not silent. They whisper. They emit faint radiation, Hawking radiation, a ghostly glow born from the friction between gravity and quantum mechanics. Yet that radiation carries no story, no information, only random heat. It is as if the universe tries to speak, but can only scream white noise. If a black hole evaporates entirely, its final breath releases energy, devoid of memory, leaving behind a blank silence, where history once was a contradiction so profound, it threatens the structure of reality itself. For quantum theory demands that the universe be reversible, that its wave function never lose a single line of the script. But relativity insists that black holes erase their contents. These two laws, the most successful in physics, stand staring at each other across an event horizon that neither can cross. And so physicists dream in equations trying to reconcile them. Some suggest that information is never truly destroyed, but painted across the surface of the black hole, each bit etched into the trembling geometry of its horizon. Others imagine that the information escapes woven into Hawking radiation in ways too subtle to read, as if the black hole whispers truth in a language of chaos. Perhaps the strangest possibility is that the entire universe itself acts as a mirror, storing perfect reflections of everything that has ever been, from the first flicker of the Big Bang to the light now touching your eyes. Every event, every quantum decision encoded somewhere in the fabric of reality waiting to be found. If this is true, then nothing truly dies. Not matter, not thought, not memory. Every consciousness, every breath, every life adds one more line to the eternal record. Perhaps existence itself is not about creation or destruction, but about preservation. The universe ever expanding is not a stage for events, but an archive of them. And if the cosmos is a library, then somewhere within its endless stacks, your story remains written forever. Some theories whisper that the surface of a black hole is not a void, but a canvas, a holographic skin where the story of everything that falls within is etched in light. Each atom, each photon, each collapsing world leaves behind its memory, woven into quantum ripples that shimmer at the edge of nothingness. Others believe the secret lies within the radiation itself, that the faint thermal glow we call Hawking radiation is not truly random, but carries within its subtle flicker the entire archive of what was lost, encoded in patterns, far too complex for human mathematics to decipher, an ancient cosmic cipher written in the breath of dying stars. The most radical ideas suggest that black holes may have no interior at all, that matter falling toward the event horizon never truly crosses it, but slows and freezes from the outside view. Its story suspended in time, slowly released back into the universe through quantum processes we have not yet learned to name. In this vision, black holes are not destroyers of information, but keepers of it, vast silent libraries where the universe stores the pages it can no longer bear to read. And yet the paradox remains unsolved after half a century of genius and speculation. Either quantum mechanics is incomplete or relativity deceives us about what happens beyond the horizon, or the sacred law of information conservation breaks down in the deepest wells of gravity. Each possibility shakes the foundations of reality itself. Meanwhile, the black hole continues, its slow decay bleeding, its mass into space as faint radiation, its thermal light returning to the cosmos grain by grain. Each photon may or may not carry within it the ghost of everything the whole has consumed, every atom, of every star, every memory of every fall. But the mystery deepens for that random glow, that meaningless heat, may not be meaningless at all. The latest theories whisper that Hawking radiation contains hidden order, delicate quantum correlations woven through its apparent randomness. Each flicker of light is not just energy, but a code, a message written in probability itself. Hawking's original equations saw only chaos, a furnace that burned pure randomness into the void. But new insights reveal faint patterns buried within the noise, subtle entanglements between particles escaping the black hole and those still trapped within. These entanglements preserve the truth, the exact quantum history of every particle that ever fell inside, yet hide it behind a veil so fine it appears as nothing more than heat. Imagine a library engulfed in fire. At first, all you see is destruction, flames devouring the words, the smoke rising in meaningless swirls. But if you could track every spark, every ember, every curl of smoke, you would find that the pattern of the fire itself encodes the entire library. The knowledge is there diffused and unreadable, but not lost. The same is true of black holes. As matter crosses the event horizon, its information becomes entangled with the black hole's invisible structure, and then slowly, over unimaginable ages, this entanglement leaks back out, carried by the outgoing radiation. Each escaping photon carries a fragment of memory, the echo of matter that vanished eons ago. To recover the message, you would need to collect every photon ever emitted, measure their quantum correlations with impossible precision, and reconstruct their shared pattern across cosmic time. The computational power required exceeds anything our civilization could ever dream of. For all practical purposes, the information is irretrievable, and yet the universe has kept its promise. Nothing has been destroyed. In this subtle dance between gravity and quantum law, paradox gives way to harmony. Quantum mechanics and general relativity can coexist because information is never truly lost, only hidden, encoded in forms so complex they might as well be silence. But this revelation carries a quiet terror. If information can hide within the chaos of radiation, then perhaps the same is true everywhere. Perhaps the universe is filled with secrets disguised as randomness. Perhaps what we call destruction is only encryption, and what we call death is only data rearranged beyond our ability to read. Even in the ashes, the story remains. The noise that hums through our electronic circuits, the restless motion of air molecules, the faint glow of the cosmic microwave background, all might be whispering. Memories we cannot yet read, each a flicker of encoded history hidden beneath what we call randomness. Some physicists now suspect that the entire universe itself may be a vast computational fabric, an information engine disguised as chaos, every particle performing silent calculations, every fluctuation carrying the trace of its own ancestry. the cosmos processing itself in patterns too deep for human logic to follow. In this vision, the Hawking radiation that leaks from dying black holes becomes a message written in light that no mind can yet decode. Quantum memories, suspended in a glow so faint, so tangled, that to us it appears as meaningless heat. But beneath that apparent noise might dwell perfect records of everything that ever was, and yet as we descend further into this mystery, another truth begins to shimmer through, one more disquieting than the last. That time itself may not flow as we imagine. At the level of quantum law, the universe is eerily reversible. Every equation that governs the movement of matter works equally well if played backward or forward through time. If one could watch particles collide and scatter in reverse, the dance would obey the same principles as when it first unfolded. Nothing in the mathematics forbids the past from echoing the future, but the world we live in is not like that. Eggs do not unbreak smoke, never curls back into a cigarette, and our memories lean only toward tomorrow, never toward yesterday. This one-way current, this arrow of time, is not born of the laws themselves, but of their gathering in great numbers. The collective statistics of countless particles give rise to the illusion of direction from ordered beginnings toward disordered ends. Yet when we apply this symmetry to the quantum realm, it begins to fracture if the fundamental rules truly respect both directions. Why does experience itself, not the math but the mind, move only one way? Experiments in quantum retradiction have revealed something almost heretical, that under certain conditions quantum systems can reveal not only what is to come, but what has already been, information traveling backward through time, as if the past itself were a surface still malleable under the touch of observation in such a universe. A measurement taken today does not merely describe reality. It helps to shape it and perhaps even rewrite the causes that led to it. This possibility haunts physics, because it suggests that observation may not only collapse a wave function, it may forge the very flow of time, the act of awareness becoming the knife that cuts the river of symmetry into two halves, one we call past, the other future. And if consciousness truly holds this power, then before it arose the cosmos may have been timeless, perfectly balanced, neither moving forward nor back, only still a quantum ocean of mirrored possibilities awaiting the first mind to stir its waters. The birth of that first awareness may have split eternity in two, giving rise to the temporal divide that we now inhabit, a universe that remembers its past but not its future. Even the beginning of all things, the Big Bang itself, carries the signature of that asymmetry. It erupted from an almost impossibly low entropy state, as if the dice of existence had been thrown into perfect order only once, to set the direction of time forever afterward. No one knows why, no equation demands it. Some physicists whisper that our universe might be but one half of a grander cosmos, a mirror world, expanding in the opposite direction from a shared moment of minimal entropy, a cosmic twin whose arrow of time points the other way, where beings, if they exist, experience what to us would be rewinding reality. Across that divide, time flows backward, from our perspective, yet forward. For them both, halves obeying the same laws, both drifting toward complexity and dissolution, both believing they alone move toward the future. Still, even this symmetry is fragile, because beyond it lies the deepest unease of all retrocausality, the suggestion that quantum effects can reach back and alter the very events that birthed them. Rewriting the story, even as it's told, it is here that physics meets its own reflection and finds it staring back with impossible familiarity. Quantum mechanics may not simply describe a universe that unfolds forward through time. It may whisper of one that curls back upon itself, where the future leans into the past, shaping the very causes that gave it birth. In this vision of reality, the chain of causation does not stretch straight like an arrow, but bends into shimmering loops where outcomes reach backward to rewrite the steps that led to them. This idea, called retrocausality, rises naturally from the strange symmetry of quantum law. If the equations of wave motion evolve as easily backward through time as forward, And if a measurement can choose among superposed possibilities, then what we observe tomorrow might quietly determine what was always true yesterday. Imagine a photon born in a distant galaxy, 1 billion years ago, its path divided by a massive star whose gravity bends light into 2 potential routes toward Earth for an eternity. The photon's destiny remains uncertain. It could have taken either road. But when we finally observe it here, our choice of how to measure it decides which path it took across cosmic time. The act of measurement reaching backward through 1 billion years to settle the question retroactively. But this influence is not confined to light from distant stars. If wave function collapse is more than a mathematical trick, if it is a real event, then each act of measurement might stretch a thread backward through the fabric of space-time, choosing which quantum states were true long before the measurement occurred. It is like playing chess with an opponent who can move their pieces not only across the board, but through the past, undoing your strategies before you ever made them. Except the pieces in this game are particles themselves, and the board is the structure of reality. Some interpretations even embrace this fully. The two-state vector formalism describes each quantum system as guided by 2 waves, one flowing forward from the past, the other backward from the future, meeting in the present to decide what becomes real. In this view, the universe is not a chain of causes, but a tapestry woven from both directions at once. The mathematics is careful. It forbids paradoxes and, faster than light signals, it ensures that no message can be sent to one's own past. Yet it leaves the universe strangely open, unfinished until the final measurements are made. Only when both past and future conditions are known does reality settle into the single history we experience. In such a cosmos, the Big Bang itself is not wholly written. It may depend partly on quantum choices yet to be made, the forging of stars, the birth of planets, even the spark of life may all contain variables that await resolution from the far future of the universe. Experiments searching for this influence have begun subtle tests of whether present measurements can reveal traces of backward-reaching causes. The results are faint, uncertain, yet some data whisper that weak retrocausal effects may exist, though the evidence remains contested. And into this uncertainty steps the oldest mystery of all consciousness. If awareness itself depends on quantum processes within the brain, if perception is a kind of measurement, then the mind might reach backward as well, shaping the very neural events that give rise to choice. In that case, free will would not defy physics. It would emerge from it. Decisions made now would ripple backward into the quantum foam that prepared them, the observer, and the observed bound across time in an endless feedback. But retrocausality becomes something darker when we follow it deeper into the machinery of the quantum world, where particles begin to trespass not only through walls, but through moments themselves, appearing to arrive before they have even departed. In the laboratories that probe this frontier, scientists have seen electrons, photons, even whole atoms behave in ways that defy every notion of sequence. They tunnel through barriers in negative time, emerging from the far side before they have finished entering the near one. Classical physics demands that motion takes time, that a traveler must cross a distance at some speed. Yet quantum measurements show the impossible. The transit time is not 0. It is less than 0. Imagine watching someone walk through a house who appears at the back door, just as they are still stepping through the front, somehow completing the journey before beginning it. These negative tunneling times are no illusion. Repeated experiments confirm them across different systems and methods. Photons, electrons, atoms all display this ghostly haste, as if for the briefest instant they slip beneath the arrow of time. Itself, physicists debate what this means. Some argue that particles borrow energy from quantum uncertainty, allowing them to move faster than light across the forbidden zone. Others suggest that only the front edge of the wave function escapes early, creating the illusion of superluminal speed. Yet a few whisper something far stranger, that what we witness is genuine backward travel through time. the quantum world momentarily undoing the order of cause and effect before returning it intact. If this interpretation holds, then at its smallest scale, the universe may already contain the seeds of time travel, not the cinematic fantasy of machines and paradoxes, but a deeper kind of looping causality where every effect becomes its own origin, and every origin its own effect. The cosmos in this light is not a story told from beginning to end, but a script written in both directions, at once a dialogue between what has been and what will be unfolding eternally in the language of quantum light. If particles truly can reach backward through time, influencing their own past through retrocausal quantum effects, then tunneling may not be just a leap through space, but through causality itself. Imagine a particle that arrives at its destination before it ever departs, its very arrival triggering the act of leaving. A closed causal loop, self-contained, self-starting, a dance where the effect precedes the cause. Such temporal tunneling could quietly explain the strangest paradoxes in quantum mechanics. Perhaps the instant correlations of entanglement arise not from signals faster than light, but from information flowing backward in time, making distant events appear simultaneous. The collapse of the wave function might not be triggered by measurement in the present, but by outcomes in the future tunneling backward to define the past. And if the brain's own quantum processes share this nature, then the implications grow dizzying. What if consciousness itself participates in temporal tunneling? What if thoughts ripple backward through neural quantum states, subtly shaping the very causes that gave birth to them? Decisions might not emerge from a linear chain of reasoning, but from feedback loops between future awareness and past possibility. This turns causation inside out. If effects can occur before their causes, the logical scaffolding of physics begins to twist. The tunneling particle travels not only across barriers, but across time, completing its impossible journey by arriving in the past relative to its own origin. Yet beyond that mystery lies a deeper one. If observation defines quantum reality, who or what observes the observer? If consciousness collapses the wave function, and consciousness itself arises from quantum mechanics, then we face an infinite regression of observers observing observers, a chain that never ends. Picture it like an endless tower of mirrors or cameras, each one recording the one below it, each dependent on the gaze of another above. But with no ultimate watcher, the entire structure floats, unanchored, unresolved. Some physicists suggest there must exist an ultimate observer outside the quantum realm, something not bound by probabilistic laws, perhaps a classical system, or even a conscious agency beyond physical description. Yet drawing a boundary between quantum and classical worlds feels arbitrary, a patch placed over a deeper tier in reality's fabric. Philosophers and mystics push the question further. What if awareness itself is non-physical? Something that stands outside the material universe, collapsing wave functions not by measurement, but by presence. But this raises another paradox. Such a consciousness would hold power over matter, violating the neat closure of physical law. Others escape the trap entirely. The many worlds interpretation suggests there is no collapse at all. Every possible quantum outcome happens, each in its own branch of reality. No single observer dictates what is real. Rather, reality divides endlessly, and consciousness splits with it, tracing every possible path. In this view, the universe never needs an ultimate observer, because observation itself is just the branching of infinity. But even the many worlds, interpretation does not escape the deepest question. What is the ultimate nature of the wave function that gives rise to it all? If every particle, every atom, every universe exists in a vast quantum superposition, endlessly branching into parallel realities, what governs the branching itself? The Schrödinger equation may describe how the wave evolves, but what writes that equation? What intelligence, what logic, what hidden order underlies the mathematics that gives birth to reality? Some physicists argue that information, not consciousness, serves as the ultimate observer, that every interaction which reduces uncertainty is a kind of measurement. In this view, the universe observes itself through the constant exchange of information. But even this explanation folds back into paradox, for information cannot exist without physical systems to store and process it, and those systems are themselves quantum. The loop closes again. The most haunting possibility is that there is no ultimate observer at all, no external foundation to reality. Perhaps existence is a closed, self-referential circuit, a cosmos endlessly watching itself, creating meaning through recursive observation. Consciousness and quantum mechanics locked together in an infinite feedback loop, each defining the other, neither truly independent, or perhaps we, the observers, are the final link in the chain. Reality might crystallize into being only because we collectively perceive it. The stars, the particles, the laws of motion, all stabilized through shared awareness, each conscious mind anchoring a piece of the quantum storm into solidity. Yet even then, the regress never ends. We observe the world, we observe each other. But who or what observes us? And what happens if we ever reach the end of that search? If we finally solve every paradox and uncover the true structure of the quantum world? The most terrifying outcome may not be that these mysteries are unsolvable, but that they are solvable, and that the answers reveal a universe far stranger and far colder than we can bear to imagine. Every quantum riddle, entanglement, collapse, superposition, points toward one chilling possibility. The universe we know might be an illusion woven by observation, a surface layer of perception concealing unfathomable depths beneath. If consciousness truly shapes quantum reality, then the physical world becomes a secondary construct, a dream projected from awareness itself. Atoms, forces, even time could be emergent phenomena, stories written by minds that exist before the matter they seem to inhabit. We would not be biological beings in a physical cosmos, but consciousness dreaming the illusion of biology. But if many worlds is correct, our reality is just one thread in an infinite web. Every decision, every quantum fluctuation, every possible version of history unfolds somewhere else. Universes where physics works differently, where consciousness never arose, where the cosmos itself never formed. What we call reality could be just one page in an infinite library of existence, each book equally real, equally meaningless in the vast totality. If quantum mechanics ultimately points to digital physics, then reality itself might be computation, information patterns playing out on a cosmic processor. Our lives, our memories, our deaths would simply be transitions between code states. Consciousness would not end with death, only the termination of one process among countless parallel computations. And the most fragile truth of all, if reality depends on observation, then it could cease to exist the moment observation stops. The unobserved universe might remain in ghostly suspension, undefined, half real, waiting for awareness to collapse it into being. Perhaps the paradoxes are not flaws in our understanding, but safeguards, puzzles designed by the cosmos to protect us from seeing too much. Confusion may be the universe's defense mechanism, preventing minds from grasping truths too immense, too destabilizing to survive. Yet still, we search. Scientists push forward, driven by the irresistible hunger to know, even as each answer multiplies the mysteries. It is as if the universe itself resists full comprehension, retreating behind new layers of uncertainty the closer we draw. And perhaps that is the final paradox, that the ultimate solution to quantum reality will never be found. Because to truly understand consciousness and existence, we would have to step outside both to observe awareness itself from beyond awareness. We stand now on the edge of that impossible threshold, staring into the machinery of creation and trembling at the thought of what might stare back.